For the same reasons that understanding decimal places is important, understanding significant figures is also important in experimental work particularly, because they allow us to consider measurement limitations when we're processing our experimental data. In IB chemistry, we firstly need to be able to count the number of significant figures in a value. And secondly, we need to consider significant figures when multiplying or dividing measurement values in a processing of our data. Let's have a look at counting significant figures first. There are three simple rules that we need to follow when trying to identify the number of significant figures in a measurement value. Firstly, any non-zero figures are always significant. And by non-zero figure, I mean any number from 1 to 9. Secondly, a zero can be considered significant if it is between two significant figures. And finally, a zero that comes after a significant figure is also considered significant if it is also after a decimal point. And if those rules sound a little bit confusing, let's try some simple examples. So in this first example, 143, all of my figures are non-zero figures. Therefore, they are all considered significant. So there's the 1, the 4, and the 3, which in total makes 3 significant figures. In example B, well, first of all, I can see that there are some non-zero figures in there, so the 1 and the 7 are definitely going to be significant. And if I look at rule number 2, I can see that a zero that comes between significant figures is also counted. So in this case, both zeros, which are sandwiched between the 1 and the 7, also count, giving us 4 significant figures in total. In example C, I can see 4 and a 2. We know they're definitely going to be significant. And there's a 0 between them, which according to rule number 2 makes that a significant figure. However, the last 0 is not sandwiched between them. And if I look at rule number 3, that 0 comes after significant figures, but it is not after a decimal point, so we are not going to consider it as significant. So in this example, we've got 3 significant figures in total. In example D, we can see immediately the 2, the 3 and the 1 are going to count as significant figures. And for the 0 at the end, I need to look at rule number 3. This 0 comes after some significant figures, and it's also after the decimal point, which means in this case it is considered significant. So in total here we've got 4 significant figures. In example E, we can immediately identify the 2 and the 3 as significant. The other zeros, however, do not count as significant figures in this case, because they come before the significant figures in my number, and therefore they don't qualify in any of our criteria. So this number has just 2 significant figures. Now in example F, we have a slightly different number. This one is written in scientific notation. And the general rule for scientific notation is that the number that we record must contain all of the significant figures in the original value. So in this case, I'm looking at the first part of my expression, where I can see a 2, a 3, a 1, and a 0, which is after those significant figures and also after the decimal place, so that's going to count as well. And because I have to show all my significant figures in scientific notation, I know that my original value must also have had 4 significant figures. Now that we have a sense of how to count the number of significant figures in a value, let's see how we apply that when multiplying or dividing these values in a calculation. So in any calculation that uses experimental data where I multiply or divide my values, I need to consider and apply 2 basic steps to the treatment of significant figures. The first step is simply to identify the number of significant figures in the measurement values you're using. And secondly, similar to how we use this in decimal places, we need to apply the smallest number of significant figures in my values and apply that to my calculated answer. And the reason we do this is because it takes into account the precision of measurements in our experiment in order to present final values to an appropriate number of significant figures. Let's have a look at 3 simple examples. So in this first example, if I stick that calculation into a calculator, I get an answer something like 3.3083. Try that again, 833, so on. However, in order to give our answer to an appropriate number of significant figures, I need to look at the 2 values we've used and identify the smallest number of significant figures in those values. So in the top value of my calculation, I've got 3 significant figures, and in the bottom value, I've got 2 significant figures, which means I need to give my final answer to 2 significant figures because that's the lowest number that I can find. For example B, if I do this calculation in a calculator, I get an answer something like 239.054 something something something. So again, in this case, because I'm doing a multiplication calculation, I need to identify the number of significant figures in my values used and then apply the smallest of those numbers to the answer. So in the first value, I've got 3 significant figures. In the second value, I've got just 1 significant figure. And in the third value, I've got 4 significant figures. Now the smallest number of significant figures there is the middle value, which has just 1 significant figure. So I need to write my final answer to 1 significant figure as well. Now example C, again it's a division calculation, so I need to be considering significant figures in my answer, and it's a slightly complicated one for reasons we'll see in a moment. Now if I do this calculation in my head or on a calculator, the answer I get is 80 litres per second. Now you'll notice I've made a small change to one of my values to highlight a key point. So let's double check the number of significant figures in my values that I used in the calculation. In the top value, I've got 1, 2, 3, 4 significant figures. And remember, all of those zeros count in this case. You can work that out by looking at the beginning of the video again. In the bottom value, there are 2 significant figures. So I need to write my final answer to 2 significant figures. And at the moment, it is only written as 1 significant figure. Now, very rarely you might come across an example like this. And the way we're going to deal with it is by writing my answer in scientific notation where I can show clearly that it has 2 significant figures. Now it seems a little bit weird to do this, but certainly if you are answering a question in an exam or you're doing your internal assessment, you want to make sure you're really consistent with significant figures if you're doing a multiplication or division calculation. And by writing this final answer in scientific notation, I can show clearly that it has 2 significant figures. And the reason I want that is because if I look at the values in my calculation, we actually need to use the smallest number of significant figures, which is 2. Now, I've probably talked a little bit more than I should have done in that last example. So as a very simple summary, when we are doing multiplication or division calculations with experimental data, we need to consider the number of significant figures in the values we're using and apply the smallest number of significant figures you can find to the final answer. Hopefully, this video is of some help.